Hi, this is James Cook of the University of Maine at Augusta, and this is the third video in a series titled, Will I Ever Use This? Which is about why the equation for a line matters in sociology and society. It's that question that I think every generation of students has asked, going all the way back to when algebra was invented. Why do I need to know this? When will I ever use this? And I know my teacher just said, because it's on the test. And that wasn't a good enough answer. I want to give you that answer myself. So to start to do that, I want to talk in this video about how that equation for a line matters. The equation y equals mx plus b, which might have been the bane of your existence if you really didn't like algebra, yet it was really important. I want to show you how that equation might matter, and I want to show you using some data that really does matter in our time. It has to do with the pandemic, coronavirus, COVID-19. So we could just think about where the virus is right now, and I'd like to show you this graph, which is the number of cases per million people right now, and by right now I mean February 8th, 2021. This data is gathered and compiled from each of the state agencies that deal with public health, either the state CDCs or bureaus of public health. They have different names, but this graph shows us where the virus is has been very strong and where it has been relatively absent, and in a comparable way by not just looking at the sheer number of cases, but the number of cases per million people, because the state of California, which has a population of about 39.5 million people, is close to 1 in 8 people in the United States, whereas the population of Maine is just a little bit more than 1.3 million people, much less than that. So how do you compare California and Maine? By looking at the cases per million people in each state. It's like a percent. So in this graph, we can see, first of all, that there are some cases that cross a bright line, states that cross a bright line. And that is the 100,000 mark, because 100,000 means that there have been 100,000 diagnosed cases of COVID-19 per million people. 100,000 is 1/10 of a million. That means 1 in 10 people in these states, I believe they're Arizona, Arkansas, Iowa, just barely Nebraska, North Dakota, Oklahoma, if I'm seeing that right, Rhode Island, South Dakota, Texas, and Utah. That's a lot of states where 1 in 10 people has been officially diagnosed with COVID-19. We can expect that there are a number of others who just never got trapped by the system, but these are just those that have been caught by the system and had that positive test. That's a lot of people infected with a deadly disease that is not only deadly, but causes a huge number of chronic conditions for many people who have this that will cripple them for life. On the other hand, we can look at some states like Hawaii, which has the lowest rate in the nation, and Maine, New Hampshire, Oregon, Vermont, and Washington State that have really pretty low cases, at least a case rate per million people. Why are some states having huge flare-ups of COVID-19, while other states are not? It's a reasonable question, and it's an important question, because this is a disease that is pretty soon going to have killed 500,000 people in this country, 500,000 people, which is, we're already far exceeding the deaths in World War II. We exceeded the total US deaths in Vietnam, well, at least 6 months ago. So why is that the case? This is the really crucial, important question. And to answer that question, what leads to higher COVID-19 case numbers in one state versus another, we can consult some stories we might tell, right? Some ideas we might have that seem to make sense. For instance, is it that in some places people are separated from one another? Is it perhaps that some states have mandates for mask wearing where others don't? And it turns out there is variation in that. Or is it the leader that we follow and the example of what that leader says and the consequences of that? Well, the neat thing about those questions is, first of all, from a sociological point of view, each of those stories is a theory. Each of them it generates a hypothesis, a prediction about what we should see, and each of them suggests a variable, not just the outcome variable, R Y, right? Which is the cases per million for a state, but suggests an X variable that might explain it or be associated with it. So if we think that people being separated from one another, just in a natural order of things, might have to do with higher COVID rates or lower COVID rates, well, we can develop a measurement of that, and that is population density. There are some places where the number of people per square mile is really high, and some places where it's really low. We could, on the other hand, take a look at another variable. Is there a state law mandating mask wearing? In order to test that, all we have to do is look it up. And third, is it the leader that we follow and the example and suggestions that the leader provides? Well, in the year 2020 and into early 2021, which is where we are on February 8th, the day that I'm recording this video. Who is that one leader in the United States that is most associated with opinions about COVID-19 most strongly? I think it would be fair to say, regardless of what side of the political spectrum you're on, that would be our former president, Donald Trump, who had a lot to say frequently and voluminously about COVID-19 on Twitter and on the national news and on the radio and in speeches and so on. So for that last variable, we could think about the percent of people in a state who voted for Donald Trump in 2020. And that might be seen as a good indication of whether that state has a concentration of people who are followers of former President Donald Trump. Well, the great thing is that for each of these possible variables, we have sources that we can use to measure this. For COVID-19 statistics, again, we can grab information through state bureaus of health, and I'm using a source called worldometers.info/coronavirus/country/US for a few reasons. The first is that source allows you also to look at other countries and do some comparative work. It's not just the United States. The second is that it very quickly, more quickly than Johns Hopkins, which does some great work, and is usually cited more often, but it very quickly updates throughout every day, the coronavirus statistics. So for state mask mandates, I've allowed a reporter to get me that information. A reporter at U.S. News and World Report has put together the states with mask mandates and the states without mask mandates. And it turns out there are a good number of states that do not have mask mandates. So only 32 do, with 18 that don't. So that's a good amount of variation. And then for the percent of the vote for Donald Trump in 2020, I've looked at the certified election results, which come from the Cook Political Report, not me, but the Cook Political Report is a conservative-leaning website that took a look at the national popular vote and the popular vote in each state that was certified. And I've used that there. And then for population density, I've taken a look at data.census.gov, which allows me not only to look at the population for each state, but also the square mileage for each state, which allows you to then look at the number of people per square mile. So when I put all of those together, the result is what you see here. This is a Microsoft Excel spreadsheet. And then it's arranged in the form of a data set. You'll notice in blue you have columns. Columns are vertical, and the column headers are across the top. And it'll tell you what's being measured. And those are the variables. Remember that variables are characteristics that you can measure that vary. And each one of these do. And in the rows you see going across horizontally, and that's indicated in green. You'll see states. There are the 50 states. I've not counted Puerto Rico, Guam, District of Columbia, and so I've only focused on states just because that's where the data it tends to be complete. So here we have 50 states. And for each of these 50 states, there are a number of variables. As a matter of fact, 1, 2, 3, 4, 5, 6, 7, 8 variables besides just the state name, which I suppose is a 9th variable. So you can take a look at this. If you would like, I will be placing this up on our course website for you to review, should you wish. There are just a few variables that I'd like you to take a look at and pay attention to. The first is one called mask mandate. You see ones and zeros for reasons that I'll show you later on. A 1 is taken to indicate a yes. So Alabama does have a mask mandate, but a 0 indicates a no. Alaska is a 0. Arizona is a 0. Those states do not have mask mandates. Likewise for Florida and Georgia and Idaho and so on. Why do I use ones and zeros? Well, it has to do with the magic powers of ones and zeros. Any number times 1 is itself, and any number times 0 just goes away. For that reason, people who engage in social research and create data sets like these use ones and zeros to indicate yeses and nos. 1 is yes, 0 is no. So, with that in mind, the great thing we can do here, another example is that we can combine these and calculate some variables. So for instance, from population, and then if I took the square mileage of each state, I could take the total population and divide it by the total square mileage of a state, the number of square miles. And you'll see that although California has one of the largest populations of the United States at 39.5 million, it's also a really big state. So the number of people per square mile just comes out to 254. Whereas Florida has a slightly lower population, or Delaware, let's say, has a really lower population, about 1/40th that of California, but it's in a much smaller space. And so its number of people per square mile is 500. Rhode Island is a really interesting example because it's the smallest state of them all. It has about 1 million people, and a very small space, though. So, I'm sorry, it is the second highest population density of all. The number of people per square mile is 1,025. The real winner here is New Jersey, which has a higher population and is also relatively small. Compare Rhode Island to Maine, where you have more people in Maine than in Rhode Island. 1.3 million people, but in a lot of space. I'd like to highlight that as a professor at the University of Maine at Augusta. And so the population density is 44. Montana, however, is, even though it has around 1 million people, is even bigger, and it comes out to a population density of 7. And then there's our friend Alaska up here, which actually has a population density of 1 person per square mile, and that's a mile by a mile by a mile by a mile. It's a box, a mile in every cardinal direction. So that's not very many people at all. Could it be that this population density that is lower in some places leads to natural social distancing? We'll find out. And in fact, let's make that the first one that we, attended to. So I could create from this a graph, what's called a scatter plot, in which we have 1 dot for each state, and you see that here, in which the y-axis, and I put it on y because it's our outcome variable, which is pretty handy, is cases per million population. And you notice I labeled that y, so you remember that's the y. And you can see the natural variation on the vertical axis there. On the other hand, we could have an x-axis. Why they're called the y and the x-axis? Because people per square mile could indicate a horizontal axis, and the numbers are between 0 and about 1,200. So you can see the variation in that axis as well. But the neat thing we can do then is that we can estimate the line that best fits this data, that is, comes closest to all those dots. And when we do that, you'll see here in the lower right the actual estimated line for that, and that is y equals negative 4.5273x plus 82,926. Okay, well, that's a lot of numbers, and a y and an x, but what does it mean? It means that we can look at, with the m, which is the slope that's associated with the x, we can look at the testing of this idea we had, that places where there were more people per square mile would have more deaths, or excuse me, more cases of coronavirus, more cases of COVID-19. Does that seem to be the case here? Well, unfortunately not. When my computer calculated the best fit line that comes closest to touching all those dots, the first thing you'll notice is that there are a lot of dots that are very far away, especially on the left-hand side of the graph. And the line is actually showing a negative slope. Now, a positive slope would indicate that as the number of people per square mile increases, the number of cases per million population would increase. But that's not what's happening here. What we actually see is the opposite. Now, that might be frustrating to you if you were a person who thought, yes, when people are spread out, they're not going to get COVID as often. because it's the opposite of the prediction, number one. And number two, it's not explaining the dots very well. A line that hit all the dots, or a line that is hit by all the dots, where the dots all come together into a line, would indicate the strongest relationship. There's a statistic that I won't ask you to know, but it's called R squared, and it indicates that only 0.26% of the variation in the cases per million population of COVID-19, state by state, is explained by population density. This is confounding for many people, including myself. I expected this to be a positive number, because as a sociologist, I know that when people come closer together, they're more likely to interact. And I know that viruses are things that spread when people interact. So how strange is that? What it says to me when I look at this graph is that there's so much variation going on at every part of this graph from left to right in the y-axis, which is the number of cases per million, that something else must be causing that variation. What could that be? Well, we have a second contender, and let's look at that contender. That second contender is whether there is a mask mandate in the state, by law. In Maine, there is, and as we pointed out before, in a state like Florida, there is not. So we can take a look at all of those states, and you'll notice that they're lined up on the x-axis on just 2 points, 0 and 1, where 0 means no, there isn't, and 1 means yes, there is. And we can then look at, for those cases in the zeros, you can see that they're scattered out there on some cases per million population. And some of them are higher and some of them are lower. And then you can take a look at the states where there is a mask mandate. And again, there's some higher and some lower. There's still a lot of variation in each group. However, the best fit line, the line that best fits, comes closest to hitting those dots, is the following: a line that is described by y equals negative 11526x plus 89,385. Now, in this case, we can look for a moment at the at that b, right? Y equals mx plus b. So b is 89,385, 89,385. Well, if you look, and you remember from high school geometry and algebra class, the b is called the y-intercept. It's where the x-intercept hits the y-intercept, which is at the value 0. So it tells you, check this out, when x equals 0, y should equal 89,385. Why in the equation do we know that? Because if x is 0, then 0 times negative 11,526 is going to be 0, because any number times 0 is 0, and 0 plus 89,385 is 89,385. Well, look at that. If you take a look at the place where the best fit line that's drawn here hits the x-axis, it hits at just about 89,000 and change, actually exactly 89,385. And so this line can tell you that the average there, the place that comes closest to all the dots, which is the average for a value, the average is 89,385 cases per million population for those states that do not have mask mandates. Well, what do we say about the states that do have mask mandates? Well, again, the equation tells us what to do, and so does, by the way, that drawn line. It says, oh, well, we're going to do something. The other piece, we're going to take 89,385 and we're going to add on whatever minus 11,526 is times x. Oh, well, when the answer is yes, the mask mandate variable was coded as 1. And that's great. That's super math magic because any number times 1 is itself. So the average, which is the point closest to all of those dots over on the right-hand side, where the math mandates are, is whatever 89,385 plus a negative number, which means minus 11,526 is. And, you know, I'm going to have to do the math really quickly, but that comes out to 77,859 cases per million people. Okay, so 77,859 cases per million people is better than 89,385,000 cases. But it's not all the way better, is it? I mean, and it's still within the same order of magnitude. This idea that just declaring a state law that thou shalt wear a mask will lead to lower COVID case rates, well, it's in the right direction, but it's only explaining, it turns out, with this R-squared statistic that tells me this, 5.6% of the variation from state to state in how many cases per million people there are of COVID. Well, what does that mean? You know, if something is overriding the number of people per square mile, right, population density, and something else is lurking out there that is causing a whole lot more variation, and that might be something else besides a mask mandate. You know, the mask mandate is about explaining a 20th of what's going on, and don't get me wrong, that's better than the 89,385 figure, but it's not explaining everything either. And the equation for a line can tell us this. It can take what two ideas that sound like, yep, that might really do it, and it allows us to say, hold on, either, you know, it's really not explaining much of anything in the case of the United States, or it's not explaining very much. 94% of the variation, 94.4% of the variation is still unexplained in how much a virus there is in a state. That tells us that something wonderful, which is so much better than simply telling stories. It allows us to test stories and say, hang on. Well, first of all, population density doesn't seem to be it. And second, the mask mandate, well, that's helping some, but it's not going to solve the problem for us. Possibly because, as you might be able to see, if you think masks work, and the scientific data suggests very strongly that they do people in a state wear masks just because they're mandated by the state? And I think our popular experience has been that they don't. People in some communities and some groups are still gathering without wearing masks. So what would explain that? And that's where we can come to our third graph, which contains a third equation for a line. And that is the percent of voters for Trump in 2020. Again, this is taken from state by state from the Cook Political Report figures. And here we still do see, you know, some variation around the line, but you can see this shape. This shape that is kind of coalescing around this best fit line. A line that is, if I have my figures correctly here, y equals 134,310x plus 14,727. And this line accounts for about 34.6% of the variation in the cases per million population. So for one variable and one variable alone to explain what happens to anything having to do with people is really actually pretty good. That's a little bit more than a third of all the variation is explained by how much support for Donald Trump there was in the state in 2020. Regardless of where you sit on the political spectrum, this is a piece of information that is it's confirming the hypothesis that it's consistent, at least, with the hypothesis that support for this national leader, former President Donald Trump, has something to do in a state with the cases per million population. 34.6% of the variation. We can take a look at that equation for a line again, and let's take a look at that y-intercept. It says that if we can imagine a state where there was 0% vote for Donald Trump, and by the way, there was none, the state with the lowest vote for Donald Trump was just a little bit over 30%. And the state with the highest percentage of a vote for Donald Trump was just a little bit below 70%. But if it's telling us if there was a state out there that had no support, 0% of the vote went to Donald Trump, that we would expect that the cases per million population, based on where that line is going, would be at about, yeah, 13,000, I do believe it would be at 14,727. There, that's where we go. And if we were able to go all the way up to 1, which is where 1 equals 100%, we could imagine that, looking at our slope, that, well, if x is 1, which is 100%, then the expected cases per million population would be 134,310 plus 14,727, which would be the no Trump state, which doesn't exist, but we can imagine it now. The everyone votes for Trump state would have a value of 149,037 cases per million. We see actually as we get up to 60-65%, there are a couple of states that get pretty darn close to that. These are the Dakotas, by the way, where there was a motorcycle rally in Sturgis, South Dakota, getting a number of people from North Dakota as well, and neighboring states like Iowa, which also has a high rate. Excuse me, actually, I just want to check that. Don't want to. Yes, that's right. Iowa does have a number. So a lot of people from Iowa coming in, a lot of people from North Dakota coming in to Sturgis, South Dakota for this motorcycle rally where just about no one wore masks. And lots of people got COVID then. So what does this tell us? It tells us that of the 3 stories that we could spin about what leads to a state having a really high infection rate versus a low infection rate, the one variable out of these 3 associated with one story out of the 3 that overwhelmingly explains most of the variation is the one where we say the states where there was a high vote for Trump seem to have the highest infection rate. It's still not explaining everything. It's only explaining about a third of the variation, right? But if we only had one story to tell, we can now say which story we ought to pay attention to. And that is a powerful ability. Whether you're predicting deaths from COVID or cases of COVID, or whether you're predicting other kinds of things like industrial pollution or support for abortion. All of those are variables, and you can explain the patterns in those and therefore understand how society seems to be working right now with the equation for a line. And that is why it matters. It matters because it can explain things that, some of them are whimsical outcomes that you might want to understand, but some of them have to do with life and death. As we approach 500,000 people who have lost their lives and have been recently at the rate of one 9/11 attack per day in on and on again and again in terms of the death toll. We can only hope it goes down. That matters. If you are a public health official, if you are a frontline healthcare worker, and you want to understand what will lead to possibly an amelioration of this, being able to test those stories matters. Now, there are more stories than this about COVID-19. We could, for instance, ask about hand washing activity and see whether some states are hand washy and other states are not hand washy. We could talk about in and out migration rates. Where do immigrants come to from places that have high caseloads of COVID, and where are the states that people don't tend to visit? Those are all stories we could tell too, but these are the stories I wanted to tell today. Now, a few of you may be wondering, hang on here, Professor Cook. You really told this story, half of it with an equation, but half of it with a graph. Why couldn't we just do the graphs? Why couldn't we just look at those and kind of get a general sense? In these cases, the graphs did give us a very good general sense of this, of whether there was a telltale pattern or not. However, there's one thing we haven't done so far, and I'm not going to ask you to do it in this class. And that is to imagine what happens if you had an equation that simultaneously tried to estimate the effect of state mask mandates and people per square mile and voters for Trump, and tried to find a line that took all of those into account. Now, in order to do that, given that our fourth variable is cases per million population, we would have to have, say, perhaps an x-axis of percent voters for Trump in 2020, a y-axis of cases per million population, but then we need another axis for people per square mile, and a fourth axis in four-dimensional space of state mask mandates. Now, I don't know if you can think in four-dimensional space and imagine a line traveling through four-dimensional space to indicate what the pattern is, but I know I can't. I just don't have the brain for it, and most human beings don't. But we can describe that with the math, and it's relatively simple math too. If you understand the idea of y equals mx plus b, where y is an outcome, x is some explanatory variable, m is a slope associated with that variable, and b is just the number that tells us where the line starts at the 0 point. My gosh, you can do a four-dimensional prediction in just one line of text. Let me show you what I mean. Imagine if we go on to the X, it leads to the Y thing, then we can think backwards and we could say, what are those other two dimensions? And we'll say, well, we'll go backwards in the alphabet and call them the W axis and the V axis. And so the V axis is state mask mandate, where 1 is yes and 0 is no. W axis is people per square mile. X axis is percent voters for Trump in 2020. And the Y axis, as before, is cases of COVID-19 as of February 8th, 2021 per million population. And the equation for that four-dimensional line is one in which we have still just the regular old Y on one side of the equation. On the other side of the equation, we have a B, which is where it all begins, with the value of Y, where all of those axes values are equal to 0, where V equals 0 and W equals 0 and X equals 0, right? Because 0 times any other number, right, is 0. So that'll cancel out all the V stuff, the W stuff, and the X stuff, and it just leaves Y equals to B. But then there's only a little complication. which is that we put in v, w, and x. We separate those, the v, w, and x with pluses, and each of those terms we multiply by its own slope, which, if it's positive, indicates that as that value goes up, so does y. And if it's 0, it indicates that as that value goes up, y doesn't do anything. And if it's negative, it indicates that as v goes up, well, actually y goes down. And guess what? It takes a computer, and I just mean a regular computer you could buy for $500 at Staples or Best Buy. If you have Microsoft Excel and you add in a data analysis pack, and I can show you how to do it, you can run a multiple regression in about 30 seconds for a 4-dimensional thinking. And the equation that is estimated is y equals negative 5664.2 for v, which indicates, right, that if y goes up from 0 to 1, that the case rate goes down by 5,664 per million population. So that's consistent with our prediction. People per square mile. Now, if you control for those other two variables, is in the right direction. And it's saying that as the number of people per square mile, which again, let's remember the units are like anywhere between 1 and 1,200, every time you go up by 1 person per square mile, you're going to add on 30.4 to the cases per million population. So now that's in the right direction. And as you think about the voters for Trump in 2020, and that percentage, right, which goes between 0 and 1. 1 is 100%, 0 is 0%. That the difference between states that vote strongly and not strongly is in the 6 figures. And that's the 170,000 and 8.1 times x. X is the percent voters for Trump in 2020. And then the intercept, where all those other axes are 0, tells us that the predicted cases per million population would be 0, which is not surprising because many of those variables are not going to get ever to 0. No state has 0 people per square mile, and no state had 0% voting for Donald Trump. What's even more important is that when you add all 3 as possible predictors, the ability we have to predict the case rate per million population goes up to 44.8%, almost 45%, which is, you know, a little bit lower than half of all the variation explained by these 3 ideas. This is the power of y equals mx plus b. This is why it matters. This is what it can do. Am I going to ask you to generate these estimates in this class? No. But what I am going to ask you to do is to start to get ready to think about that. Because as a social science senior, if you became a major, which I encourage you to do, you could collect a data set like this yourself. You could run the model, and once you collect a data set like this, which doesn't necessarily take a long time, and once you formulate your ideas about what might matter and test them, to test them, it takes a computer 30 seconds. And you could have your senior project ready. Also note that in this class, I'll be talking about this idea of variables that are measured and have units that we understand, outcomes that we care about, and differences in what the average outcome is for, you know, different groups of people who fit in different categories based on their experience described by different independent variables like x's or v's or w's. Keep that in mind, and that's why not only would I like you to have an idea of algebra and a familiarity with the equation for a line in this class, but also an appreciation for the power that it can have in explaining things that matter. Matters of whimsy, matters of joy, matters of pain, and matters of death. Um, this is true not just for sociology, but for all of the empirical sciences. And when your high school teacher told you to nail down the idea of an equation for a line, they might have told you or they might not have told you, but that's what this is all about. That's what algebra is useful for. It's for taking a world in which we have a lot of great ideas about how things might work. We have a lot of stories about how certain conditions might matter in affecting other things. But now we have a tool to actually test that and to adjudicate, which really is a fancy word just meaning judge, between all those different possibilities. Now we know, at least for today, February 8th, 2021, and at least just for these variables, we have a story that we can tell. We have some answers that we can provide. And if we want to make a difference in the world, it gives us something to think about. For the University of Maine at Augusta social science program, I'm James Cook, and thank you so much for watching these videos.